In the last video, I showed you how to calculate an equilibrium constant from standard free energy data. In this video, I'm going to show you how to calculate standard free energy data from an equilibrium constant. And the reaction that we're going to be looking at is the dissociation of hydrofluoric acid or hydrogen fluoride, HF, into a solvated proton and a fluoride anion. And the equilibrium constant for that reaction is 6.6 times 10 to the minus 4. Now you'll notice that this equilibrium constant has a subscript attached to the K. We're not just saying it's a K, we're saying it's a Ka. The subscript simply tells you what kind of an equilibrium you're talking about. Mathematically speaking, there is no difference between a Ka, a Kb, a Kf, a Ksp, or any of the other types of K that you may ever run into throughout your chemistry career. They are all equilibrium constants. They all fit into the equation map in exactly the same place. The only thing the subscript gives you is a little bit of information about what kind of a reaction are you talking about. A stands for acid. So this is the equilibrium constant for a reaction in which something acts as an acid, in which something gives up a proton. And in this case, the acid that we're talking about is HF. You will already be familiar with Ka, at least in passing, because we mentioned it in Chem 1000 when we presented pKa as a way of measuring the strength of different acids. And we said that an acid with a low pKa was a stronger acid compared to an acid with a higher pKa. And the pKa is simply the logarithm of the equilibrium constant for the dissociation of the acid, and then times -1, so that the majority of pKa values are positive. This means that if you have an acid that dissociates very readily, that releases a lot of H+, you're going to have high activities of products. You're going to have a large Ka value, and when you take the logarithm of a large Ka value, you get a large number. And when you multiply that by -1, you get a large negative number. The strongest acids have pKa values in the ballpark of -10. Weak acids are going to have very low activities of the products in this sort of an equilibrium. You're not going to get much dissociation, so you're going to have a really tiny equilibrium constant. You might have an equilibrium constant in the 10 to the minus 10 or 10 to the minus 20 range. And when you take the logarithm of that, that will be a number from -10 to -20 in my example. And when you multiply that by -1, you get a number between 10 and 20, which would reflect a weak acid because it's a higher pKa. So oftentimes you'll be presented with pKa values instead of Ka values. And the simple reason for that is that our brains like small numbers better than numbers that are either extremely large or so small that we have to use scientific notation with relatively large times 10 to the minus something numbers. If you need to get to the Ka value from the pKa value, we can rearrange this equation to get equilibrium constant Ka equal to 10 to the minus pKa. And so therefore, if we're saying that strong acids have low pKa's, then we're saying that the strong acids have large Ka's. But all that said, this is still just straightforward thermodynamics, and we can still work with our equation map. There's nothing special about the fact that we're talking about an acid, not in terms of the math. So we've been given an equation that is balanced. We've been given an equilibrium constant. We're being asked to calculate a free energy of formation of our reactant in this case, and we've been given some other standard free energy of formation values as well. So if we go back to our equation map, We've been given the equilibrium constant, and we're trying to get to a standard free energy of formation value. So to get there, we're going to have to go by way of the standard free energy change for the reaction, and it's going to be a two-step process. So first up, we calculate our standard free energy change for this reaction, which we can do from that equilibrium constant. So delta G naught is equal to negative RT ln K, or negative 8.314462 joules per mole Kelvin times 298.15 Kelvin, because as with everything else in this chapter, we are talking about 25 degrees C. We were not explicitly told that, except for the fact that we were asked about standard, and standard means 25 degrees C or 298.15 Kelvin, times the natural logarithm of our equilibrium constant, which is 6.6 times 10 to the minus 4. The kelvins cancel out. And that's going to give us plus 1.82 times 10 to the 4 joules per mole. But normally we report standard free energy changes in kilojoules per mole, and our standard free energies of formation have been given to us in kilojoules per mole, so it would be helpful to convert this value into kilojoules per mole as well. And so to do that, we multiply by 1 kilojoule per 1,000 joules, and then the joules cancel, and that gives us a standard free energy change for this reaction of plus 18.2 kilojoules per mole. So that's step 1 finished. Now we move on to step 2. In step 2, we know that our standard free energy change for a reaction is going to be equal to the standard free energy of formation of our products minus the standard free energy of formation of our reactants. And what we're trying to solve for is this term here. So if I rearrange my equation, I get standard free energy of formation of HF equal to standard free energy of formation of the proton plus standard free energy of formation of the fluoride minus standard free energy change for the reaction. And then I plug in my values. So we have 0 kilojoules per mole plus negative 278.8 kilojoules per mole minus 18.2 kilojoules per mole. And that should give us a standard free energy of formation for aqueous hydrogen fluoride, aqueous hydrofluoric acid of negative 297.0 kilojoules per mole. Thermochemical calculations are all about keeping yourself organized. They're all about identifying what do I know, where am I going, how do I find a path